So we've been calculating slopes at a particular point, and we've just drawn some derivatives. So if we actually plot the different slope values, we can actually see that there's a pattern that evolves. And that pattern means that there must be some function that is the slope function, or a function that calculates slope. So how do we find that function then? We want to find that general function. Okay, so that general function we know exists. And we're going to find it in this way. So before we used that fixed point here, so for example, we use a fixed point of 2, and at that point, we're just going to find a secant line. So we're going to choose a point arbitrarily close to 2 and do a limit and make those 2 points come together, and we end up finding the limit of that slope when it becomes 0 over 0. Now we're going to essentially do the same thing, but we're going to change it slightly. Instead of having some fixed point 2, to find the slope specifically at 2, we're going to make that a general point x. And then we're going to generalize this slope for some point at some general x. So I'm just going to pick a point arbitrarily close to x, do the same thing, make my run become 0, and I'm going to end up with the limit. And that limit's going to be expressing the slope values at some point x, and that x can be anywhere along this line. So we then just generated the slope function, or what we're going to start calling the derivative. The derivative. So how do we set it up? Well, these are my coordinates here. So I've got my x plus h. For x squared, I'm going to use y value for x is x squared. The y value at x plus h is going to be x plus h squared. And in general, it's going to look like this. The y value at x plus h minus the y value at x divided by the run. And we're going to let the limit as the run goes to 0. So basically, it's the same thing as we've been doing before, except now instead of this fixed point of 2, we're going to generalize that point of x. And what we're going to end up with is the slope function, okay, or equation that calculates slope. So for this particular problem here, we're going to look at y equals x squared. So there's our graph. We're going to pick these 2 points. So I'm going to get the rise between these 2 points. So it's going to be x plus h squared minus x squared. So there's our rise. Our run is still going to be the difference between those 2 points, which is h. And then I'm going to let the limit as h goes to 0. And that's going to calculate the slope at some point x, or a general point x. So if I follow through with this, then I'm going to end up with the limit as the run, or h goes to 0. I'm going to expand this out. X squared plus 2xh plus h squared minus x squared all over h. And notice that the x squared, you may have noticed this before with the numbers, that the y coordinates seem to just cancel out. And that kind of makes sense because we actually only want the distance between. We just want this rise. So we don't really need this distance in here, which is the original y coordinate. So we cancel out those y coordinates. Okay, so what's left over? I'm going to continue on here. I'm going to show the steps here. As h goes to 0. So I'm going to end up with 2xh plus h squared all over h. And what I've done is I freed up this factor of h. So I have a factor of h in the numerator, which is going to get rid of that divide by h in the denominator. So I'm going to cancel out those factors. I'm going to show one more step. I'm going to have the limit as h goes to 0 of 2x plus h. I don't have any divide by 0 anymore. I can evaluate this limit, and this limit works out to be 2x. So what this 2x represents is it's a function, okay? It's the function that actually calculates the slope for any position x. And we write it like this: y prime, that prime means the slope function of y is equal to 2x. And this, I can just now, instead of finding out, slopes of each individual point, I've now generalized for any x, which means then I can actually plug in different x's to calculate slopes on the original y function. So let's just double check that this is actually a good function, a good equation. So if I take a look at the x squared equation, the x squared function, I'm just going to make a quick check here. I'm just going to make a table of values. So I'm going to have x, and I'm going to use my y prime, okay, my slope function. And does this slope function actually give me relevant slope values? Okay, so let's take a look at 0. At 0, I have a slope of 0. Okay, so I'm just going to put 0. If I plug into my slope equation, yeah, I get a value of 0. Okay, that seems to work. Okay, what about for positive x's? Okay, so for positive x values, for all positive x values, it looks like I have positive slope up here. Okay, well, if I plug in positive for here, I get positive slope value. That seems to be correct. And as x gets bigger, it looks like I'm getting more slope. Okay, and as x gets bigger, my slope values increase. That is very consistent. That's consistent with the formula. If I look at negative x values, so on this side of the line, so that part of the curve, I'm sloping down. Okay, so that makes sense because my slope value is going to be negative when x is negative. And furthermore, the more negative x I get, the bigger negative slope I get, so steeper it gets, and which is true for that parabola. So this slope function seems to be giving me relevant slope values for this particular graph. So this generalization, this 2x function, is a function that actually calculates slope. And one other thing that I'm going to just point out, and this is something we kind of alluded to a lot earlier. This parabola has differences that are linear. Okay, so the changes in y were linear. Notice that the derivative, or the change in y over change in x, is also linear. Okay, so those things are in fact related. Okay, the change in y and the fact that we have a rate of change that's matching that, going from quadratic to linear. Okay, that's leading us to think that this is a very relevant result for this slope. Okay, so this y prime then, we're going to be fairly confident that this is actually going to calculate slope values for this graph.